The most advanced artificial intelligence chips in America can become useless for an ordinary reason. The electrical system feeding them may not be ready. A new AI data center can be designed and built in roughly 2 years. In some parts of the United States, getting enough new grid capacity connected can take 3 to 7 years. That mismatch is turning electricity into a competitive constraint. One of the fastest tools for giving the grid more flexibility is battery storage. Batteries can absorb electricity when supply is available, release it during peaks, support a data center through disturbances, and reduce how much instantaneous capacity a site demands from the grid. But many of the cells best suited to that job come from the same country Washington is trying to remove from strategic technology supply chains, China. That does not mean Chinese batteries are secretly running every American AI server. Batteries do not generate electricity, and most data centers still depend primarily on the grid, generators, and dedicated power projects. The real issue is subtler. America is trying to build compute faster than it can build transmission, substations, turbines, and new generation. Storage can compress part of that timing problem. Yet, the global storage cell industry that can manufacture huge volumes cheaply is concentrated in China, so the AI race may contain a second race underneath it. Not merely who makes the fastest processor, but who can manufacture the physical equipment that lets thousands of those processors receive reliable power at industrial scale. The scale of the demand shock explains why this matters. U.S. electricity consumption barely grew for years. Now data centers are helping push demand upward again. The Department of Energy has cited estimates that data centers could consume as much as 9% of U.S. electricity generation by 2030. Other industry estimates used by Reuters put the upper range much higher, near 17%. Those forecasts differ because nobody knows how quickly AI campuses will be completed, how efficiently chips will operate, or how much proposed capacity will connect. But utilities do not have the luxury of waiting for a perfect forecast. A single large AI campus can demand power on the scale associated with heavy industry. Battery storage attacks one specific part of that problem: timing. Imagine a grid connection as a highway entrance with a fixed number of lanes. A data center may need high power during certain periods, even though some hours leave more capacity available. A battery charges when the electrical highway is less crowded, then discharges when demand rises. It does not create another highway. It makes better use of the one already there. That distinction is critical. Batteries cannot replace power plants for a continuously operating gigawatt-scale campus. Most U.S. lithium battery projects are designed for only a few hours of discharge. They are excellent at shifting peaks, stabilizing frequency, pairing with solar, and bridging short interruptions. They are not a magical multi-day energy source. Yet even that limited role is becoming enormous. The United States installed roughly 58 gigawatt-hours of battery storage in 2025, a record. Developers are now examining batteries not only beside wind and solar farms, but at data centers themselves, where fast response can be especially valuable. And the chemistry that dominates this market is not the nickel-rich formulation favored by many American electric vehicles. It is lithium iron phosphate, or LFP. LFP gives stationary storage several advantages. It is cheaper, avoids nickel and cobalt in the cathode, offers long cycle life, and works well where a battery can sit in a large enclosure instead of being squeezed beneath a car floor. China spent years scaling this chemistry, while North American battery investment leaned heavily toward automobiles. That matters because a battery factory is not a printer where operators simply select a different chemistry from a menu. Industry executives told Reuters that converting an existing plant to LFP can require around 18 months and several $100 million. And even if America builds the final battery pack domestically, the cell is only one layer of the dependency. The harder question is what sits upstream of that cell: cathode materials, graphite anodes, processing capacity, manufacturing equipment, supplier qualification, and the cost advantage created by scale. That is where the battery problem stops looking like an import problem and starts looking like an industrial system problem. And this industrial system is where China's advantage becomes much harder to replace. Stationary storage increasingly revolves around lithium iron phosphate, or LFP. For an electric car, reducing battery weight and squeezing more energy into a smaller pack can be extremely valuable. A battery sitting beside a substation or data center faces a different equation. It can be large. It does not need to move. What matters more is cost, cycle life, reliability, thermal behavior, and how cheaply thousands of identical cells can be manufactured. China built enormous capacity around exactly that equation. By 2025, more than 600 gigawatt-hours of battery cells were shipped globally for stationary energy storage. Benchmark Mineral Intelligence found that the 10 largest suppliers accounted for roughly 90% of those shipments. Every one of those 10 suppliers was headquartered in China. That does not mean America cannot manufacture storage batteries. Domestic capacity is expanding quickly. Automakers have underused EV factories. Korean manufacturers are increasing American production. New LFP plants are being planned or converted from existing lines. But final assembly is only the visible end of the process. A cell factory depends on precisely processed cathode material, anode material, electrolyte, separators, manufacturing equipment, quality control systems, trained operators, and suppliers capable of delivering enormous volumes with extremely consistent chemistry. Even a tiny defect rate becomes expensive when a project contains millions of cells. That manufacturing experience cannot be imported through a blueprint. Scale produces another advantage. A manufacturer building hundreds of gigawatt-hours can spread engineering costs across more cells, negotiate cheaper materials, optimize production equipment faster, collect more operating data, and pressure suppliers for lower prices. Those savings compound. The result is not simply a cheaper Chinese battery. It is an industrial ecosystem designed around manufacturing batteries cheaply. CATL demonstrates how large that ecosystem has become. The company says it sold 121 gigawatt-hours of energy storage batteries in 2025 alone. CATL also cites industry data giving it about 30% of the global energy storage battery market. That means one Chinese manufacturer shipped roughly twice as much stationary storage battery capacity in a year as the entire United States installed during the same period, and China is already moving beyond conventional LFP. In 2026, CATL announced a 3-year agreement to supply 60 gigawatt-hours of sodium-ion batteries for energy storage. Sodium-ion technology still has limitations, particularly lower energy density than the best lithium-ion cells. But stationary storage cares less about weight. Sodium is abundant, and the chemistry could reduce exposure to some lithium-related material constraints. For America, that creates an uncomfortable possibility. While U.S. companies are trying to localize today's dominant storage chemistry, Chinese manufacturers are already commercializing another one. Washington is responding aggressively. Section 301 tariffs on Chinese lithium-ion batteries used outside electric vehicles were scheduled to rise to 25% in 2026. Natural graphite from China was also targeted for a 25% tariff. The objective is understandable. If storage becomes essential infrastructure, relying permanently on a strategic competitor for the cells and materials inside that infrastructure creates economic and geopolitical risk. But tariffs create a timing problem. Making Chinese batteries more expensive does not instantly create an American battery factory. Reuters reports that Chinese products represented roughly half of U.S. battery imports between 2021 and early 2025. Meanwhile, U.S. storage installations are still accelerating as utilities add renewables, grids face congestion, and data center developers search for faster ways to secure reliable power. America therefore has to perform two difficult tasks simultaneously. It must install far more storage, and it must restructure where that storage comes from. There are signs that this transition has started. Tesla has sought American-made LFP cells from LG Energy Solution. Automakers are redirecting some EV manufacturing capacity towards stationary storage. U.S. battery assembly capacity could expand dramatically before the end of the decade, but cells account for only